Hello and welcome to ENGR 330 Fluid Mechanics, the recitation on Chapter 9. Let's look at some problems from Chapter 9. This is problem 13 from your book. The viscous fluid flows past a flat plate such that the boundary layer thickness at a distance 1.3 meters from the leading edge is 12 mm. You're asked to determine the boundary layer thickness at a distance of 0.2, 2 and 20 meters from the leading edge. And you're asked to assume laminar flow. So in this problem, we're not sure what the fluid is. However, we know that delta scales as kinematic viscosity times x from the leading edge over the free stream velocity raised to the power half. So since we don't know the kinematic viscosity and the free stream velocity, and we know that those are constants, so we can remove this constant of proportionality by putting a constant and putting that it is a square root of x. Okay? And now the point is we need to determine this constant c. For that, we know that delta is 12 mm at x equals 1.3 meters. So substitute that in the above equation, we get delta over square root of x, so 0.012 meters square root of 1.3 meters, so c turns out to be 0.0105. So now that you know the constant c, you can determine delta at x equals 0.2 meters, which would be 0.0105, which is your constant, times x, which is 0.2. So if you do that, you get 4.7 mm. And as we learned in class, as you move along the plate, your boundary layer thickness will increase. So at delta x equals 2 meters, if you do the math, it will be 14.8 mm, and delta at x equals 20 meters would be about 47 millimeters. Okay? If you knew the fluid kinematic viscosity and the velocity, you can determine the constant easily. However, in this problem, we were given the information in a different way. But this is how you do it. Let me write this. This is 20 meters. Okay, let's look at another problem. You're given a laminar boundary layer velocity profile is approximated by the velocity as you have shown, and you're asked to show that this profile satisfies the appropriate boundary conditions and also use the momentum integral equation to determine the boundary layer thickness. So like in the previous problem, since it was a laminar flow, we could use that approximation and do it. Similarly, again, we know that this is a laminar flow, right? So we know that U over U is 2 minus Y over delta times Y over delta for Y less than or equal to delta, and U is the free stream velocity for Y greater than the boundary layer thickness. So if you go back to page 499 in your book, let's define capital Y as Y over delta implies U over U will now be in this new variable as 2 minus Y times Y for Y, capital Y, lying between 0 and 1, and U over big U is equal to 1 for the second for this boundary velocity profile. So we get y less than or equal to 1. Let me rewrite this. This should be y greater than 1, okay, because it has to be above the boundary layer thickness. So I had an error there, so that's why I have to correct it. So it should be y greater than 1. Okay, so now you define a function g of y as 2y minus y square and g of 0 as 0. Okay, so once you get y over delta in terms of big Y, right? I'm writing this function as g, and it becomes 2 times capital Y minus y square, right? And for the no slip condition, g of 0 is 0, which is satisfied, and also g of 1 should be 1. So you can see that when you substitute the big Y as 1, you get 1. So both of these check. And also dg over dy at y equals 1 should be equal to 0. So 2 minus 2y, if you do the differentiation, at y equals 1 will indeed be 0. So this satisfies the appropriate boundary conditions. That is, no slip at the wall and no velocity gradient as you move away from the boundary layer. So in part B, we are asked to determine delta. So again, you can refer this calculations or theory in your book. Delta is 2 nu C2 times x over u C1. Okay. So you have two constants here, C2 and C1. That means you need two different equations to solve for C1 and C2. These are highlighted in your book. Let's pull up those equations and determine C2 and C1. Then we will determine delta for this velocity profile. So C1 is defined as integral 0 to 1 g of y times 1 minus g of y times dy, and if you put in and integrate it, okay, this should be pretty straightforward for you guys. You'll determine C1 as 0.133. Similarly, C2 is defined as dg dy at y equals 0. This is pretty straightforward. Do the differentiation for g and substitute y equals 0. You'll determine C2 as 2. Okay, so we know that C1 is 0.33 and C2 equals 2. Let's go ahead and substitute in the previous formula for delta. So delta equals square root of 2 nu x over u times 0.133. Okay, or I can do a little bit of algebra here where I do this, where I multiply and divide by an x inside, and you'll see why that helps. You can see that this guy here is your Reynolds number, okay, and if I do 2 over 0.133 and take the square root and simplify and get the square root of x square is x, so if I get it on the other side, I get delta over x as 5.48 divided by square root of the Reynolds number, which is based on your x along the flat plate. Okay, so this is your final answer in this problem. So if you are given an x, you can then determine, and also your free stream velocity and the type of fluid, you can then determine precisely what this boundary layer thickness would be as you are at different locations on the plate. Okay, so this is how you perform this particular problem. Let's look at another problem. The drag coefficient for a newly designed hybrid car is predicted to be 0.1. That means we are given CD as 0.21. The cross-sectional area of the car is 30 square feet. So you're given A, 30 square feet. You're asked to determine the aerodynamic drag on the car when it is driven through still air at 55 miles per hour. So you're also given U, which is 55 miles per hour. So the drag, which is a force, is CD half rho U square A. So you know CD, you know the density for air. You can find this in the tables, and you must convert 55 miles per hour into feet per second, which would be 80.67 square times this cross-section area, which is 30. So you'll then determine the drag coefficient, or sorry, in this case, the drag as 48.8 pounds. Okay, this is a simple calculation. However, you should know what you're given in the problem and then just apply and find the drag. The key step also here is to convert miles per hour to feet per second, just to be consistent with the units. Okay, let's look at another interesting problem. A sphere of diameter d and density rho s falls at a steady rate to a liquid of density rho and viscosity mu. If the Reynolds number is defined based on the fluid as rho diameter of the sphere times the free stream velocity over mu is less than 1, show that the viscosity for the fluid can be determined as shown. Okay, and when your Reynolds number is way less than 1, this is known as creeping flow. And from your book, you can find the drag coefficient for a creeping flow. So let's try to write the force balance for this sphere. So you have the buoyancy force, you have the weight of the sphere, and you have the drag. So if you do a force balance, weight should be equal to drag plus the buoyancy force. Now let's try to write the weight, drag, and the buoyancy force in terms of the variables given in the problem. So you know that weight is mass times acceleration due to gravity, right? And I can write mass as volume times density, and now we are talking about the sphere, so it will be density of the sphere times the volume of the sphere, 4 by 3 pi r cube, or r is d over 2, so this is what you end up with. Okay, and then similarly the buoyancy force, you learned that it's the density of the fluid times acceleration due to gravity times the volume. So it would be rho g 4 over 3 pi d cube over 8. Okay, now we have to determine the drag, which is d. So drag, like in the previous problem, is the coefficient of drag times half density of the fluid u square times the cross-sectional area, and CD for Reynolds number less than 1 for a sphere, CD is 24 over the Reynolds number, and we are given what the Reynolds number is defined as, so substitute that. Okay, and remember this D is drag and this D is diameter. Okay, alright, so now I can write this as, if you simplify it, you'll get 3 pi du times mu. Okay, so now let's go ahead and substitute it into our equation where W is drag plus the buoyancy force. So I get rho s 4 over 3 pi d cube over 8 g minus rho g 4 over 3 pi d cube over 8 if you get the buoyancy force onto the left hand side, and if you put in the drag on the right hand side. Okay, so now if you further simplify it, I get 4 over 3 pi d cube over 8 g rho s minus rho over 3 pi du, and I'm solving for u or mu, the absolute viscosity. If you simplify this, mu turns out to be d square g rho s minus rho divided by 18 u. Okay, where d here is diameter, which is what we are asked to prove in the problem. Okay, so let me write this. This is your drag, this is diameter, again this is your diameter, just to make sure you understand what we are putting. Again, this is drag, this is diameter, again this is diameter, this is diameter, and this is again diameter of the sphere. Okay, let me also write here, this is your diameter. Okay, so hence we proved what we are asked to do. So we can find the viscosity of the fluid based on the diameter of the solid, the acceleration due to gravity, density difference between the solid and the fluid, and the velocity. Okay. Okay, let's look at one last problem. A Piper Cub airplane has a gross weight of 1750 pounds, a cruising speed of 11,115 miles per hour, and a wing area of 179 square feet. You're asked to determine the lift coefficient of this airplane for these conditions. So at cruising altitude, the lift will be balanced by weight. So this is your lift. So that means it will be equal to the gross weight 1750 pounds. And the lift coefficient is defined as the lift force over half rho u square A. In this case we know L, we know the density of air, u square. Make sure you convert this into feet per second since you are given miles per hour, and you know the area. So if you determine this, you'll get this as 0.288. So this concludes the recitation for chapter 9. Please review chapter 9 carefully and try to understand very important concepts in the external flows, and good luck.